Hi and welcome to this video from the differentiation section of the Year 2 A-Level Maths course, and this is the last of our videos that are linked to chain rule, although there is a whole bunch more differentiation still to come. This is the last one linked specifically to the idea of chain rule, and this one is much more of a contextual one called connected rates of change. So we're going to be having a look at doing some problem solving with chain rule. So here we go. What chain rule does is links together multivariable problems. So the key idea here is we're going to start looking at problems where we can start describing the variables in the problems, or describing each component of the problem as a rate. And so the only way to really get our heads around it is to have a look at an example. So what we've got here is a cylindrical fish tank, and we know we've got water. We're told we've got water flowing into it at a rate of 100 centimeters cubed per second, and we want to find an expression for the rate and change of the depth of water in the tank. Okay, so there's a lot of information in that question there that we've got to extract. So let's just break it down and do it step by step. And we'll start by defining the rates that which we're talking about. And the first one comes from that statement there. So it's the rate at which water is flowing into the tank, and that is going to be dV dt. Change in volume over change in time. How is the volume changing? Well, there's an extra 100 centimeters cubed per second going into the tank. Sometimes these ones are a bit tricky to spot, but the clue is there potentially in the units. So if you have a look at the units, there they go. We've got units, which is volume, so that's the dV there, and we've got seconds, which is time, so that's the dt. So that kind of helps you figure out exactly what rate we're referring to. So that's the first bit. The next bit we've got to figure out, and we're told that's 100. The next bit we've got to figure out is we need to know, or what we're being asked to find, is the rate of change of the depth of water in the tank. So the rate of change of the depth of water is, if we refer to the height of the tank as h, so that means we need dH by dt. How is the height of water in the tank changing over time? So we've got dV dt, we need to find dH dt, and we've got to kind of connect these two things together with chain rule, so we need a third thing. And this is going to be our connecting variable, which is going to come from where? Well, here's our chain rule. Our dH dt, the thing we need, is dV dt times by something. Now, you'll notice on the bottom here we've got a dt, but on the top we need dH. We've currently got dV. So we need that dV to disappear, and we need the dH to appear. So the way we can do that is by saying, well, let's put a dH on the top. So let's get that. And therefore we're going to need dV on the bottom, because those dVs will then cancel out, leaving us with the dH dt that we need. So that's the idea. Let's keep on going now and have a look at what we've got. So there's our chain rule. Here's our linking rate. There's the rate that we know. So what we're going to need to know is, we're going to need, well, how are we going to get this dH dV? Well, that thing is going to come from the formula for the volume of the tank, because the volume of the tank, which is that, V equals pi r squared h. So if we differentiate V with respect to h, we're going to get dV dH, and that's the thing that's going to allow us to link here. The other thing we've got to notice is that in this formula here, we've got pi r squared h. R, we would normally regard that as a variable, but in this particular case, what we've got is, so, well, because this is a cylindrical tank, R will be fixed for whatever size tank that we've got. So we can say that R is going to be a fixed value, pi clearly is a fixed value, so h is our variable. So essentially when we differentiate this, we're just going to end up with pi r squared. Right, so now we've got dV dH, now we can start putting it all together. So we've got dH dt there's our dV dt, that's the 100. The dV dH is going to come from there, but you'll notice we need dH dV, so what we've got to do, we've got to flip dV dH upside down. So I'm going to need that. Okay, and so therefore now I just times those two things together, and the first part of the question says, find an expression in terms of R for the rate of change in depth of water of the tank. You know what? There it is. So dH dt, how is the height changing compared to time? So how's the height changing each second? Well, each second the height of water in the depth of water in the tank is increasing by 100 divided by pi r squared centimeters per second for whatever value you've got for R. Now the second part of the question says, well, Okay, what is that value? If we know that the tank has got a radius of 15 centimetres, how quickly is the water rising up the tank? Essentially, how quickly is it filling up? So if R is 15, dHdt is going to be 100 pi over pi times 15 squared. And there you go. So water is rising up that tank, or the depth is increasing by 0.141 centimetres per second. So the tank's not filling massively quickly because, let's face it, it's a big old tank. Right, that's the first one done. Let's have a look at another example. So here we go. We've got an ice cube and we're told that it's got side length x and it's melting at a constant rate of 0.032 centimetres cubed per second. First thing says find the rate of change of the surface area when the side length of the cube is 8. Okay, so again, here we go. There's our rate, 0.032 centimetres per second, so that's volume per second, so that's dV dt, which is that one. The thing we're going to need to find is dA dt, and we're going to need it in terms, because we've got it in terms of the side length, which is x, which is going to be 8, so we need dA dt in terms of x. So how are we going to get to this one? Well, if it's not immediately obvious, I would always start off with just thinking, well, what do we know? Well, we know from the volume, we can get dV dx, and from the surface area, we can get dA dx is 12x. Now, we seem to have ended up with 1, 2, 3, 4 things linking together here, or potentially being used. Let's see what's going to happen. So we need dA dt. So let's go for, we'll put an A on the top, so that's going to come from dA dx. Now we need the x's to disappear, so I've used this one here to get the dx's to cancel out, so I'm now left with dA over dV. But I don't want dV anywhere near that, so I'm going to need dV to cancel out. So I'm going to use this one up here to do that. So if we do that, and there we go. So what now we've got is all three of those things. So this again is its kind of extended chain rule, and all the different bits are cancelling out to leave us with the bits we want, which is dA dt. So now we've just got to cobble all this together. So dA dx is 12x. dx dv, that's going to be from here, 1 over 3x squared, and the dV dt is coming from here. So we end up with all of that. Okay, and so therefore we've got our expression for dA dt in terms of x, which is minus 16 over 125x. So what it's saying is the surface area is shrinking over time. Well, clearly it's going to because it's melting. And when the side length of the cube is 8, the surface area is shrinking at a rate of minus 2 over 125 centimetres per second. Again, not particularly fast. Right. Part B, suggest reasons why your answer might not be particularly reliable. So this is standard stuff in any modelling question. It's always going to be, well, why might it be that your model is not particularly reliable? Or what issues have we got? Well, off the top of my head, things we could think about, possible reasons could be, well, the rate at which the ice melts might not be constant. So what we're saying there is if we've got a much larger cube, it might be the ice melts more slowly, and then when it gets much smaller, it's melting at a faster rate, very possibly. It might not melt uniformly, as it wouldn't remain as a cube, so what you'd tend to find is at the corners, when cubes melt, they tend to get rounded off. So you tend to get more melting happening at corners, and you might get more melting happening at the edges rather than in the middle of the faces. So the ice isn't melting in a uniform. And then also it might be the rate of melting. This value up here might not be fixed. It would depend on the temperature of surrounding air, and this would only remain constant, presumably if the temperature of the surrounding air remained constant. So when it comes to modelling assumptions, you've just got to come up with anything that might seem intelligent or appropriate given the context that you're working within. Okay, that's that one done. Let's move on and let's have a look at an exam style question. So here we go. We've got a container that's in the shape of a hollow inverted right circular cone. Basically means a cone that's upside down. And the total height of the container is 25 centimetres. The radius of it is 15. And we've got water flowing into it. And obviously when the water flows in, essentially the volume of water is also going to be the shape of the cone, but a smaller cone. And so the radius of that smaller cone of water is r, and the depth of the water is h. And first it says, show that the volume of water in the cone is given by V equals 3 pi h cubed over 25. Right, okay. First thing to notice is if we're going for volume of a cone, which is 1/3 pi r squared h, it's got an r in it. And this expression here does not have an r in it. So the first thing we're going to have to do is try and get rid of that r, which means we need to try and express r in terms of h and do a substitution. So how can we do that? Well, let's have a look at it, and let's have a look at the by using similar triangles. So if we have a look at the triangular cross section, so there we've got that triangle there on our cone of water, but for the full size cone we've got that triangle, and clearly because one will be an enlargement of the other, this angle here at the bottom is going to be the same. These are similar triangles, so if they're similar triangles, the ratio of the sides are going to be the same from one triangle to the next, so we can say that r over h will give us the same value as 15 over 25, and therefore that gives us r equals 3/5 h. We did it using similar triangles. You could have done something related to the tan function with that one as well. You'd have ended up in the same place. So what we've got now is we know that r is 3/5 h. Let's substitute that back in here. There we go, making sure we're bracketing the 3/5 as well. So that then gives us 1/3 pi times by 9 over 25 h squared h. And there you go, there's the 3 pi h cubed over 25 that we were after. Okay, that's the setup part of it. We haven't got to the connected rates of change bit, but let's get to that now. We're told water flows into the container at a rate of 16 centimetres per second. So here we go. We've got a rate of 16 centimetres per second. We've got a volume, so let's start off, well, we know we're going to use this. Let's start off by differentiating that. dV dh is going to be 9 pi h squared over 25. We've got our rate at the top there, that's dV dt, which is 16. And we need the rate of change of h, so that's going to be dh dt. And so dh dt here is going to be h dv times by dV dt. And so again, we've got that idea of having to flip one of these upside down. Right, so that's simple enough to do. So that becomes 25 over 9 pi h squared times by 16. And then when h is 10, I didn't worry about too much about simplifying that. I'm just going to get when h is 10, let's bang that into there. There it goes. So we've got 900 pi on the bottom. And that becomes 4 over 9 pi centimetres per second. And there we go, that's our question sorted.